Quite a while ago, I did a video describing what the anisotropic reflection function does in the Blender 3 series. But since then, the principled BSDF has changed quite significantly in the 4.0 series. So I figured it was time to do an updated video on anisotropic reflections in Blender 4.3. Anisotropy is a term that refers to a bias in direction. You'll see the term used in various parameters, from volumetric scattering to subsurface scattering, and in our case today, reflections. Isotropy, on the other hand, is the opposite of anisotropy and is generally the default state for a scattering function where a scattering event occurs in a random way. Anisotropic reflections are often seen on machined metallic components and on other things like Christmas ornaments, where the small-scale patterns, or strands, that scatter light cause it to reflect in a biased way. You can think of each of these strand patterns as having their own specular reflections, and the result is apparent stretching of reflections along the surface. This biasing of reflections usually happens perpendicular to the strand direction. In Blender 4.3, anisotropic reflections are managed in the specular section of the principled BSDF. The anisotropy parameter controls the strength of the bias, while rotation adjusts the strand direction. Anisotropy affects not only the specular highlight from direct light sources, but also affects glossy reflections. In modern ray tracing architectures, including cycles, specular highlights and glossy reflections are processed within the same shader layer, making the anisotropy function influence both as a unit. So let's take a look at a Blender file that will illustrate what anisotropy is, but we're going to do so without using the actual anisotropy feature. Let's take a look at this very simple scene. I've got a torus shape, and I've got it just in material preview mode here, and I've got one of these default HDRI images reflecting in our material. To make this really obvious, I'm going to come over here and increase the roughness a little bit so that this becomes a little bit more apparent. When I begin to back out, you're going to see concentric rings appearing, and as we get farther and farther out, you're going to see the appearance of this anisotropic-like reflection going across the surface. But there's technically no anisotropy here, it's just that each of the rings has reflections that we would tend to call specular reflections appearing and forming this emergent type of reflection pattern. So we're thinking of each of these rings as being a strand, and the configuration of strands produces this anisotropic reflection, and Blender cycles can mimic this process at a material level. So let's take a look at a simple example where I have just a basic default sphere with the default material applied to it, and I've already set up a partial material that I call anisotropic strands. We can see that I've got basically 3 specular highlights because I have 3 area lights in the scene. Down in the left view, I've got a bitmap that I've already generated that consists of nothing more than alternating white and black bands. That's going to just visually simulate for us strands as they're mapped to the object. And I have those right here as lines vertical.png. When I take this and map it directly into the principled BSDF for this material, those obviously appear. And they map onto the sphere using the sphere's default UV coordinates. Let's modify the sphere to create a flat top. And this will help us to see the anisotropic effects as they're often seen on mechanically generated objects that have flat surfaces. So I'm going to marquee around, say, this top area, switch over into vertex mode, select one of these, period. We're going to move the pivot to the active element SZ0. So we've gotten that flattened out. Okay, and then we can see that the strands just continue across that flat surface. So let's come down and convert this from a visual set of strands mapped to the object into something that's going to functionally produce what I call faux anisotropy for this demonstration purpose, to understand how strands are actually going to produce this effect. So if we come down, I have another bitmap here that is just a version of this that is blurred, so it'll produce sort of a nice smooth flowing bump for us. So let's remove the bitmap here. And I'm actually going to take the color of the object, the diffuse color, and remove it down to black. So all we're seeing are these specular highlights. So let's come down and create a bump node, Shift A, and then we'll do a bump, and we'll add that right there. And then we're going to drive this bump data into the height map for bump. A thing to note, if you're new to Blender, the distance value is what we want to control here. And this is one of the weirdest default settings that I can think of. This default setting is essentially equivalent to a meter's height. It's the most impractical default value ever. So we're going to start this at 0.00001 as our starting point. So let's drive this in. In fact, let's take this and move it, both of these, closer to our principled BSDF so that we can kind of see the relationship. We take this into normal, and then let's zoom in, and we can see a mild effect. So let's come in and begin increasing this value, and let's do a 5 as opposed to a 1, and we'll begin to see an increase. But let's start driving this incrementally up, 0.12. So I'm just fractionally increasing this value. And at first, we're not going to see a huge difference, but as this value increases, we're going to begin to see the effect of an anisotropic type of behavior emerge from this. So let me do it in larger values now. And there we go. So this is just an emergent behavior of the anisotropic type of behavior from a bump map. We actually haven't turned on anisotropy yet. Okay, let me go one more to really drive that home. Now, we want to consider strand direction next. So the strands as they appear right now would produce the kind of anisotropy you would see on a lot of Christmas ornaments as an example. But this wouldn't produce the effect you would have, say, of a circular machining process on metallic parts of, say, a hard body model of some sort. So what we need to do is rotate the strands by 90 degrees. If I go into edit mode for this object, select everything, let's come down to the UV editor, and I'm going to select all the UVs for this object here. In fact, let me turn off overlays so that this is really obvious what's happening. R key, and I'm just going to begin rotating the UVs relative to the bitmap that's generating the bump, which is generating our full anisotropy, until we get down to a 90-degree rotation. And this is the emergent behavior that we get. And this is the kind of thing you would expect to see on many types of anisotropy for circular machined types of objects, all being generated by these circular strands. Now, when Blender is generating this using the actual anisotropy feature, these strands are procedurally generated by an algorithm. This just illustrates what's happening algorithmically. So let's jump over now and actually use the proper anisotropic function now that we have sort of a conceptual understanding of what's happening with strands. So we're going to remove the bump and the bump node, the bump bitmap, and we're going to return to this default position. In fact, I'm going to go properly into ray tracing right here. Otherwise, the material preview doesn't simulate anisotropy. We have to be in proper ray tracing for this to happen. So we're going to zoom way down here to the specular area, and we're going to come and turn up anisotropy. Let's just take it up to a value of 1 as a starting point. We can see what happens. So the default behavior is for those strands to have been mapped longitudinally north to south on the object. In order to rotate the strands by 90 degrees, we have to come down to anisotropic rotation and set it to 0.25. So the way that the value is mapped is that 0 is 0 degrees and a value of 1 is 360 degrees. So 0.25 is the equivalent of a 90-degree rotation. So we come and put in 0.25, and then we get our rotation of the strands to produce this. Now let me come in and move the lights a little bit. Let's let me come over to the lights, and I'm going to use Light Wrangler here, and I'm going to press Tab so I can actually change the light's position interactively. It's such a great add-on. And then you can see the effects as I move the light on that object. And this pattern at the top is typically the kind of pattern you would see on circular machine types of objects. So let's jump back to our sphere and look at the values down here. Right now we're using just the default behavior where it procedurally generates these strands projected down onto the object by default through the local z-axis. So you can see right here I've got local set up as my coordinate system. Let me turn on overlays back for this object. Well, what if you want a different axis for your projection? This is where we can change the default behavior by using a tangent node. Now, Blender uses the term tangent for what I've been saying and calling strands. So just think strand, tangent as being equivalents for this function. So let's press Shift and A, type in tangent to find that. And when we plug this in, it's going to produce down here to tangent, it's going to produce the same result because this is what the default values are being used. Now let's also talk about really quick. I want to revert to something. The anisotropic value of 1.0 is basically the equivalent of what I had done of increasing the strength of the bump map to increase the strength of the faux anisotropy I was producing. So if I decrease this right here, you can see it decreases the strength of the anisotropy as if I were lowering the bump value. It's essentially kind of a similar type of thing. Blender has two different modes for determining strand direction for an object. This radial projection is a good default for a lot of objects, but you may need a more sophisticated way of doing it, and we can map strands onto an object using the object's UV map. So that's the second method. Let's go ahead and reset our values. Let's go ahead and just take both of these back down to 0 to return the object to its isotropic default. Now, if you remember when we were testing this object out, let's go into edit mode, we actually had rotated the strands here by 90 degrees when we were mapping the bitmap onto the object, so we could see the effect of rotating the strands on the object. So we need to return these UVs back to the default state. So I'm just going to press R and I'm going to rotate these back down to a 90-degree angle. Remember, strands are determined going vertically along the V direction of the UV map, which is exactly why I generated that initial bitmap with the black lines going up and down. So let's come back in, and now that we've gotten the UVs back to the default state, let's change over to UV mode, and it's automatically chosen the only UV map that we have for us. So then we just come in and we take anisotropy and let's just turn it back up to 1 by default. So here again, this is the default behavior when your UVs are mapped on a sphere using its default UV map. We can reimagine that if we just turn back on. Let's bring the bitmap over here that we used. You can see that the anisotropy matches the default mapping of these strands onto the object. Okay, so let's go ahead and rotate the UVs. We need to come back into edit mode. Let me just turn off overlays so we can see this. Come down into the UV map editor, R key, and we're going to rotate the UV map so that the strands get mapped 90 degrees. And there we go. We get the behavior that we actually are going to want a lot. I actually wish they would change the mapping of the default strands because I think this result is much more common. And so then all we'd need to do if we want to see it is we can just come in and remap the lines. And there we go. So the UV map has rotated the projection of the base color and the strand direction, and they match. Now, another way of doing that is leaving the UVs the way that they are and then just using anisotropic rotation. So let's do that. Let's come back in over here. Let's take our UVs and return them back into their default state. And then we'll come over here and change anisotropic rotation, which makes the strand lines not go along the V direction, but along the U direction by 2.5, which is the equivalent of 90 degrees, and we get back to that. So kind of once you understand what's going on here, these values are predictable. So now let's jump in and take a look at a couple of real-world examples, because this has been very abstract up until this point. So let's go ahead and jump in and take a look at this in a file that I already have partially set up. We have these small metal dials here, and we'd like to go ahead and configure them for anisotropy. I've already got a material assigned. We can take a look down here that there's a single material slot with this single material, and when we take a look at it in a rendered state, it's just sort of a flat-looking metal. I've got two geometric features here that kind of give a sense of anisotropy, but those aren't really the anisotropic effect. So let's come down, let's pause the renderer, and let's come down, take a look at the principled BSDF that we have. And when we come down to the specular layer, we have anisotropy and anisotropic rotation. So the first thing that we need to do is we need to figure out what the local coordinate system is for this object. So let's come in and turn off interactive rendering and make sure that you have your transform orientation set to global. Then we just look at what the axis is that we want to project the radial strands through. And it is the local y-axis. But by default, if we don't put a tangent node in, it's going to apply it along the z-axis. So we need to switch that. The first thing that we're going to do is turn up anisotropy all the way, and then we need to remember to configure the rotation to 0.25, which is going to be a very common thing that you want to do. So it switches the direction that the strands are being projected, longitudinally or latitudinally. Shift A, and let's come over and type in tangent. We want it to be in radial. That's the default projection mechanism. Let's tie that in, and we want it to be projected along the y-axis. Then when we have that done, we can come over and take a look at it, and there we go. See, that was pretty straightforward and simple. One thing to note when we take a look at the roughness will have an interplay with the anisotropy. The lower that you take this, it will tend to start minimizing the effect of the anisotropy. So by the time you get down to a perfectly smooth surface, it won't have much of an anisotropic effect. So just sort of keep that in the back of your mind. Let's do the same thing for the back of the watch face, this blue area, this dark blue area in here. It's basically set up as a metal. So when we take a look at it, you can see it's got this color right here that is in metallic mode. Let's go ahead and convert this over into anisotropy. So again, we're looking in the local orientation, local coordinate system actually. So we want to project along the local y-axis. So we turn on anisotropy all the way, set our rotation to 0.25, Shift A, tangent. And then we just want to configure that to match the y. It's in radial, which is correct, and we tie that in. And then when we take a look at this, let's go ahead and turn on perspective. Then we can see the effect of the anisotropy there on the back of the watch face. So let's go ahead and set up the other two dials, and we're also going to convert this over into a UV map scenario for generating the anisotropy, but that's also going to allow us to modify the anisotropic reflections to have a grain pattern to them. Let's go ahead and set this up so that we have this dial in the other locations, but the one on the right is going to have a bit of customization to it. So we need to be careful about how we set this up. So the first thing that we need to note is the one on the right is going to have a red material that goes around the perimeter, but the left and the bottom one will just have the anisotropic metal across the entire surface, but I only want to have one object that we can do instances of just to manage just a single data set. So let's come down to the material properties, and we note that we have one slot here, and we have one material assigned to that slot. Let's increase the number of slots here, and let's come back to the top one, and we're going to note that there's a little icon right here that gives us object versus data. And this is really important for what we're about to do. the material can be assigned to the object data block at one of two levels. It can be more deeply integrated at the object data level, or it can be sort of dropped at a higher level on top of the instance and object when it's in object mode. And that gives us flexibility to have multiple instances of a single object, but assign different materials to those instances. If we come up to the Edit menu and then down to Preferences, under Editing, you can see it says Link Material to Object. We don't want it to go to Object Data. We want it to be an object. So that's how I have my preferences set up. You can change it over here, but it's easier just to have it there at the beginning. So let's come into Edit mode, Tab key. So right now, if we come over here and we do select of our top slot, it has all the polygons assigned to it. So we need to set some of the polygons to one and some to the other. I'm going to come to the edge and double click to do a loop, and then expand the selection to about there. So these polygons, I want to go to the new slot. We're going to assign those. Okay, but for now, I'm just going to go ahead and give the same metal to both slots. So if I deselect and then I come up to the top slot now and I do select, it's just the interior versus the bottom having the polygons for the outside. But it's the same material for both. Well, that's great, because now I can come over and let's select, I'm going to take the A off. Let's come over here and do a select hierarchy, because the dial itself is a child of the dial backing. And let's do Option D to duplicate it, X, bring it over. Now I've got this empty right here that has the position that I want. So Shift S, cursor to selected, and then I'm going to delete that empty. And then we'll just come over back to this, Shift S, and then take this object, selection to cursor to move it into the location. Let's do the same thing for the bottom down here. Shift S, cursor to selected, I'm going to remove that. Construction object, come back up here, and let's do a select hierarchy, Option D, and then select just the backing, Shift S, selection to cursor. So now we have these three objects sitting right there in place, but now for the one on the right, let's come down here to the bottom. So remember, it has the outer selection for this bottom one right there. So let's come over here and change the material assignment on this. Come down. I already have a material here called Small Red Dial with Text, and we'll assign it on this one. Tab leaves Edit mode, but now it only changes it on that one. But these are still instances of the same object, so I only have to worry about one data set to work with. Okay, so now the fun part. This metal still has the anisotropy applied using the radial method, and we're going to change that now. So let's come back to the original one, and we need to create a UV map specifically for this purpose. So let's switch over to the UV editing mode, and you can see that right now we have one UV map, which is just a projection of the UVs onto the UV map itself. So we can come down just one UV map. In fact, I'm going to come over here and call this original UVs, something descriptive. Since it's the only map there, anything that references UV maps is going to reference that regardless of the name that I change to it. But I'm going to duplicate that. We're going to call the second UV map Anisotropy UVs. They look the same when I switch between them because it just simply duplicated the original UVs. So let's regenerate the UVs. I'm going to come down to the bottom, and we need to do this in a little bit of a different way. In Edge mode, I'm going to select a single loop here. Let's isolate this so that we can see down in the middle. I don't have any geometry in the middle. I've left that as a hole. So these edges right here can be assigned to a mark seam so that when we unwrap it, it will open that up, and that needs to happen, and it will become apparent in a minute. So let's go ahead and select all of these, come up under UV, and we're going to do angle based. It can really be any of them. Angle based will work just fine, and it has now given us new UVs that look very similar, but it's opened these up here, which is what we need. So now we just need to align these so that we can capture the UV generated strands if you want to think about it that way. And we need to align these to that vertical strand orientation. So I'm going to come over to particular just a UV polygon right here, and we need to change it a little bit so it's square, so at least the edges are aligned. So we'll come over to edge, and I'll take this one so it's really clear what we're doing in edge mode, context menu, and then we're going to do an align auto. It'll figure out which axis that's closest to, and then you can do Shift R, and just to make sure, Shift R. Now we're going to make sure that this is selected, but then press the A key and it will select all the polygons, but it will leave that one as the active of all the polygons. And that's what we want, because bringing up the context menu, we can do follow active quads and it will reset the UV map so that each polygon has that same sort of aligned relationship. So that is perfect. S key, and I'm just going to scale this down so that it's basically right within the UV space, and this is what we need. Now, when we use the UV map method, the UVs will use those vertically aligned V strand directions. But it will also do something else for us. It will allow us to generate a procedural texture that we can also map in a very easy way vertically, but then it will wrap it around the object. So let's jump back over into shading, and let's come over now and reset this to the UV map method. And then we just pick the UV map that has the UVs that we want. Let's jump back to the main object. And then when we take a look at this, it's going to look pretty much the same. It's going to return the same results, but the anisotropy is being generated because of the strand direction being captured by the UVs that we specifically just set up. So let's go ahead and give it this grain pattern and repurpose this second UV map that we just generated called anisotropy UVs. So let's go back into wireframe and let's look at the material I already have set up down here. In fact, let me bring this a little bit closer. I already have a noise texture set up with the parameters that I like. Let's take a look at that. In fact, let's come in. I'm going to isolate this again. And we can take a look at this by doing Shift and Control, and we can see what that texture setup looks like. So I kind of generated it so it looks like kind of a metallic grain, but we want it to wrap around, obviously, the object in the same direction that the strands are going of the anisotropy. So by default, we have it assigned in UV mode, but this isn't going to allow you to choose the UVs. So let's go ahead and remove that. Shift A and type in UV map. And we can then come in and specifically decide on that anisotropy UVs, and we just tie that in, and now those go around it in exactly the same way that would define an anisotropic reflection. So now we just need to come over here and set this up so it's functioning as the base color. There are a couple of ways that we could use this to make it a grain pattern appear in our anisotropy, and I'm just going to kind of use the easiest method. So what we need to do, let's move this back a little bit, is I've already got the color, the base color that's defining the density of the metal, if you want to think about it that way. So let's do Shift A, let's do Mix Color, we'll put that right there, and I'm going to drag this color that we're already using down to the bottom, and then we'll take Factor from the noise, which is just a grayscale version of it, up to the top here. And we've got it in mix mode. So let's go ahead now and preview this. So Shift and Control and click on that. Didn't change radically, but it is mixing. So if we come over and we take a look at this, if I drag the factor all the way to the left, it only shows A. If I drag it only to the right, it only shows B. So I'm going to pull this back just a little bit to maybe about right there in terms of the interaction. This is now going to be the base color that drives the appearance of the metal. So we just need to take this result and drive this back into base color. And then we just need to hook the principled BSDF in this mix shader back into the material output. So just so you know, this component up here is just the letter stenciling. So we're not really looking at that. But now let's come back to the main object. So we're going to back out and we can take a look at this. and it will begin to show a bit of a grain appearance in the metal that I kind of like. It's a subtle feature, but it just adds a really nice bit of realism having that subtle grain texture in there. And it matches the anisotropy, which is defined by the UV map capturing strands in the UV editor, if you want to think about it kind of that way. So I hope you found this to be a useful tutorial on using anisotropy in Blender 4.3.